So slide 1 here. It is the fact that common static electricity involves charges that are in the nanocoulomb to microcoulomb range. So uh, billionth of a coulomb to a millionth of a coulomb charge, and we'll soon define what we mean by coulomb in this regard. So it is the case that your fundamental charge, E, use a little e to symbolize electron, is 1.602 times 10 to the minus 19th coulombs. Big C, capital C, is the symbol for coulomb, just like capital N was the symbol for newtons, capital J for joules. Capital C is what we mean by coulombs. All right? And every individual unit of charge has 1.602 times 10 to the minus 19 coulombs. And so the first person to measure this directly was a guy named Millikan, the oil drop experiment. You could, in fact, there's a whole movie on that. We won't watch it, but PBS, Nova, all that, they do all these great science movies. And so, in fact, I think today, or was it yesterday, was the anniversary of the periodic table. Melindev did it 100, 150 years ago, something like that. Anyways, so that is a definition. So this is a notes thing. I didn't specify this in the other lecture, but this is the definition of the fundamental unit of charge. So one little electron doesn't have very many coulombs. If you actually had 1 coulomb move through something in 1 second, that's 1 ampere, and that will kill you if you're on the other end of that, right? So it's a lot of charge, okay? A lot of charge. So we have this definition, and this kind of problem really is a conversion. Okay, so we're going to use fancy forms of 1, or that railroad track kind of conversion method that you're most familiar with in chemistry. And so how many electrons? Well, I'm going to ignore that it's a negative 2 nanocoulombs because it doesn't matter whether it's negative or positive. I'm counting electrons. So I have 2 times 10 to the minus 9th coulombs. All right. And there's 1 electron for every 1.602 times 10 to the minus 19th coulombs. Okay, well that means the coulombs in this case drop out. And if you do the number crunching on this right here, you'll get 1.248 times 10 to the 10th electrons. Simple conversion. Start small, it gets more complicated as we move forward. So simple conversion using this fundamental unit of electric charge, okay, that's been empirically verified for a very, very long time now. Now, what's it? That's ELEC, electrons. Okay. How many electrons do we get? So 10 to the 10th, that's, what is that? That's 10 billion, roughly. All right, so roughly 10 billion electrons for a minus 2 nanocoulomb charge, which is not a lot of charge, but it is a lot of electrons, a ton of them. All right. How many electrons must be removed from a neutral object to leave a net charge of, and I left out the number here, so I guess I'll have to write that in. The net charge that we're looking at is going to be 0.5 microcoulombs. Sorry about that. So if we're going to remove electrons and leave a net charge of 0.5 coulombs, how much must be removed? Well, let's figure out how many electrons are in half a microcoulomb. So once again, we would do our same basic. I have 0.5 times 10 to the minus 6 coulombs, because that's what a microcoulomb is. And I'm going to divide it by 1e per 1.602 times 10 to the minus 19 coulombs. Coulombs drop. Do the math. You should get 3.121 times 10 to the 12th electrons. So 3 trillion electrons. Okay, in that regard. So these are just really conversions. There's no formula here. It's just knowing how to convert quantities from one unit to another, because there's only so many coulombs per electron and vice versa. So relatively simple problem. Moving on. If 1.8 times 10 to the 20th electrons move through a pocket calculator during a full day's operation, how many coulombs of charge moved through it? Okay, so this is pretty simple. I'm starting with 1.8 times 10 to the 20th electrons, okay? And there are 1 electron per 1.602 times 10 to the minus 19 coulombs. And this problem is just going the other direction, really. If that many electrons move, how many coulombs are we talking about? So just multiply these two numbers. It's going to get us down to a power, basically something in the tens, because the 20 and the minus 19 are going to leave us with 1 power of 10, some multiple of 10. And in this case, it's 28.84 coulombs. I guess so. It's number of coulombs. So with the negative, it will apply to other measures. Electricity coulombs is just a count of, right. So they have negative charge, but they have some amount of coulombs associated with them. Right. All right. Up the ante a little bit here. So 2.5 gram copper penny is somehow given a charge of negative 2 nanocoulombs. That's what 10 to the minus 9 would give me. How many excess electrons are on the penny? All right. So once again, we're going to have 2 times 10 to the minus 9th coulombs. And if you keep doing this thing that we've done a few times before, then we're just going to get, I think we already had an answer essentially the same as that. Another 10 billion electrons or so. So that's not hard. By what percent does the excess electrons change the mass of the penny? Okay. So how would we go about paying attention to that? Well, the mass of an electron is 9.109 times 10 to the minus 31 kilograms, okay, per electron. And I have 1.248 times 10 to the 10th electrons. So I get a mass of 1.137 times 10 to the minus 20 kilograms. That would be the mass of those electrons, the 10 billion or so electrons. All right. So what percentage do the excess electrons change the mass of the penny? Well, now I'm just going to divide that by the mass of the penny, which is 2.5 times 10 to the minus 3 kilograms. So those units are going to drop out, and we'll have a number, let's see, 4.548 times 10 to the minus 18, and that means you would equal 10.548 times 10 to the minus 16%. That's a really small percentage. As you might have guessed, this really isn't going to amount to much. The excess electrons on a penny are going to pale in comparison to the mass of the penny, because each one of these electrons is 10 to the minus 31 kilograms, and the whole penny, before you added the electrons, was, a thousandth of a kilogram instead of good grief, whatever minus 31 power is in billions and billions and whatnot. What's that? Yeah. So relatively simple problem. Again, no pat formula, just quantitative reasoning and doing basic conversion factors. So you're having to pull some old knowledge here. All right. Continuing on with the pity theme. Copper penny, given a charge of 4 nanocoulombs, how many things are removed? And we're going to get a similar answer. So for 4 times 10 to the minus 9 coulombs, 1.602 times 10 to the minus 19 coulombs per electron, and you will get 2.497 times 10 to the 10th electron. So keep getting something in the 10 billion range, which is shouldn't be surprising. If no more than 1 electron is removed from an atom, what percent of the atoms are ionized by this charging process? All right, so we're dealing with copper. If you were to look up copper, its atomic mass would be 63.4546 U, and that would be times 1 point. These are all things you have to get out of a table. Okay. And so this is going to get us to 1.055 times 10 to the minus 25 kilograms. This wouldn't be any different than the kind of things you did in chemistry, so I'm trusting you remember or can retrieve that sort of stuff. Or we could have just come out of the box with, here's the mass, of one of these atoms. All right. Number of atoms in a penny. Well, if that's how much one atom in copper weighs, and I have still a 2.5 gram, so 2.5 times 10 to the minus 3 kilograms. And how many atoms are in that? If it's all copper, we'll be dividing by that thing we just obtained. And of course, subtracting a negative from that is going to come out with a large count. So we're going to have 2.37 times 10 to the 22 atoms in the penny. It's a lot of atoms. Okay. 10 and 22 is 100 billion times 100 billion. There's 100 billion galaxies in the visible universe, each with about 100 billion stars. Some of them have a couple 100 billion stars. Some will have a little less than 100 billion. Hundreds of billions of stars per galaxy, hundreds of billions of galaxies, 10 to the 22 stars. So this is on par. One dumb little penny has as many atoms as there are stars in the visible universe. Okay, so just kind of to give you a perspective of what we're dealing with. And then I think it wanted to know, we want to know the percentage, or it does want to know the percentage, what percent. There we go. So we're going to take our 2.497 electrons and this number of atoms and divide them. So 2.497 times 10 to the minus 10th electrons per the number of atoms. And that's going to get us to 1.504. As a number, it'd be times 10 to the minus 12th. As a percent, it's 10 to the minus 10th percent. So it's basically 1/10 billionth of a percent. An insanely small number of electrons relative to the whole. Okay, but you get a lot of bang for the buck out of that sort of thing. All right. So these first few problems are just largely review of stuff not only from prior courses but other courses than physics. What's that? Yeah, we want to know what percent of the atoms are ionized. So the number of electrons that got ripped off per the number of atoms they got ripped off from. That would be the percent ionization of it. Okay. Slide 5. Suppose a speck of dust in an electrostatic precipitator has a trillion protons in it, net charge of -5 nanocoulombs, which is a lot. How many electrons does it have? So first, an electrostatic precipitator, that'd be something you put on top of a chimney stack on some power plant that's belching out smoke, and you can literally scrub the smoke clean before it leaves. Basically, you charge the particles, the soot particles as they're coming up, and then another plate attracts them by opposite charge, and you remove the bad stuff from the smoke. We did a ton of it. As you know, I worked on a submarine, spent 500 days of my life, split up into 6 equal chunks, and we would make air and breathe it. And of course, you breathe out CO2, and you better clean that up, otherwise everyone suffocates. So we have precipitators that only scrub CO2 and whatnot from the air. They let the oxygen go through, but not the CO2. All right. So, anyways, another relatively simple problem here. We're going to have what is it? 5 nanocoulombs. 5 times 10 to the minus 9th coulombs divided by 1.602 times 10 to the minus 19th electrons per coulomb. And you're going to get 3.121 times 10 to the 10th electrons. And speck of dust in it and a net charge. All right. So the precipitator has 10 to the 12th protons in it and a net charge of -5 nanocoulombs. Okay, so this is the number of electrons due to the net charge, but I have to add to it the 1 times 10 to the 12th electrons. And when you do that, you get 1.0312 times 10 to the 12th electrons. So there's the negative and the positive charges. The total number of electrons, or not electrons, let me be clear. Glad I caught that. Some of the fundamental charges are due to the electrons and the excess charge, and some of the fundamental charge units are due to the protons already there in the precipitator. The sum of those two sources of fundamental units of charge would be the total number of fundamental charge units on it. All right. So these are a lot of repeat offenders, just different ways to look at the charges. And after these next few, we start to get into some force calculations. So bear with me. Just trying to pull together understanding these atomic structures based on your chemistry knowledge and whatnot. So 50-gram ball of copper, net charge of 2 microcoulombs. What fraction of the copper's electrons have been removed? Each copper atom has 29 protons, and the copper has an atomic mass of 63.5, like we've seen before. So atomic mass it's not 456, it's 546. And then using this conversion factor, it'll be somewhere in the back of the book. It's probably in your chemistry book if you still have that. And so we get the same number. I think we had the same number a minute ago. So number of copper atoms is going to be that 50 grams, or 50 times 10 to the minus third kilograms of the copper ball itself, divided by the mass of each individual atom in copper. And that gives us 4.739 times 10 to the 23rd atoms in this copper ball. Number of electrons, okay, is 29 times the number of atoms. So 29 times this number up here will give you 1.374 times 10 to the 25th electrons. What fraction of the copper's electrons have been removed? Well, we have, it's a 2 microcoulomb net charge, all right? So I need to get that microcoulomb net charge into something that's in fundamental charge units, all right? So 2 times 10 to the minus 6 coulombs times another way, and I think I'm almost certain that this is in your book, you can use, instead of doing that calculation manually where you divide by 1 over the 1.602, you can just use 6.242 times 10 to the 18 electrons per coulomb. That's basically 1 over the 1.602 times 10 to the minus 19, okay? You can just use that directly. And of course, that drops out. And then you can just divide by this number we just got here, 1.374 times 10 to the 25th fundamental units. So now you have a fraction because E over E is just going to be some pure number. And you get 9.083. As a number, it's 10 to the minus 13th. As a percentage, it's 10 to the minus 11th percent. What's that? Yes, that's what that's from. Each copper atom has 29. Um, oh, I put electors instead of electrons. uh, the afternoon. So we get a really small percentage again. Unsurprising. How many coulombs of positive charge? I think this is the last one before we start doing force calculations. Yep. Are there in 4 kilograms of plutonium, given its atomic mass is 244, and that each plutonium atom has 94 protons? Okay. So 244 U for atomic mass. And we've already seen this number a bunch of times now, 1.66 times 10 to the minus 27 kilograms per atomic mass unit. That means that I have a whopping 4.05 times 10 to the minus 25 kilograms in this atomic mass unit. And if I have 4 kilograms of plutonium and this atomic mass for it, then that means we're going to have 9.877 times 10 to the 24th atoms in this chunk of plutonium. I think a kilogram is it 2.2 kilograms per pound or the other way around? I forget, and I need caffeine. So we have this number of atoms, and if I multiply that by 94, then I'll get 9.284 times 10 to the 26 protons. What's that? Yeah, something like that. So we're it's going to be 8.8 plus pounds of plutonium, right? That would be a lot. You could get in trouble if you had any plutonium. All right. So lots of protons, 10 to 26 protons in this thing, and how many coulombs of positive charge? Well, I'm going to take that number, 9.284 times 10 to the 26 protons. And protons they're also a fundamental charge unit. And there are 1.602 times 10 to the minus 19 coulombs per proton. So protons and electrons have the same fundamental charge, all right? And so this boils down to a lot of coulombs. 1.487 times 10 to the 8 coulombs. And so that's 100 million coulombs, roughly. 10 to the 8 is, right? So we have 1.5 of those 100 million coulombs. Simple, easy peasy. So that was like 8 in a row of essentially the same sort of thing. You need to be able to go back and forth in this unit with some of that atomic structure knowledge from chemistry. So now let's get into some force calculations. it is almost time to quit. So, all right. So you have a lab, the sim lab, that's due Sunday. In that sim lab, if you follow the lawmaking scheme that I taught you last semester, a couple of you will have to catch up on that. Um, you'll be able to form Coulomb's law, force law for electricity. Now I'm going to write it. It's in your book too, because we're going to use it. But on the back end, you're going to attempt to craft this force law. So Coulomb's law, electric force. Let me get my pen going here. So it is the case that electric force, I'll say F sub E, there's this constant K, which it's 9 times 10 to the 9 times 10 to the ninth, and it's going to be the product of the two charges in the force interaction and the square of the distance between them. So R sub 1, 2 for the distance between charges 1 and 2. And there is also an electric field, and any field force, and we hit this in first semester, is always the force associated with that field per unit whatever quantity is what is associated with that interaction. So the gravitational field strength is force per unit mass, Newton's second law. Electric field strength will be electric force per unit, well, charge, because charge is what causes an electric force interaction, not the mass. Mass is associated with gravity. That's why it's force per mass for gravitational field strength. But it's going to be, if I write, electric force per, say, charge 1, then that means it's going to be K Q2 per the distance squared. And that's how we define the electric field. Okay? The electric field for charge 2. So every charge, like we were talking about yesterday, is either spitting out lines of force or sucking in lines of force, plus or minus. I oversimplify and cheat a little bit with the lingo, but you get my point. So we're going to use this definition of the electric field, and of course this definition of electric force. We're going to use those in this next wave of problems, all right? And so here's where it begins to get a little thick. All right, so I have two charges, plus 3 microcoulombs and plus 12 microcoulombs are fixed 1 meter apart, with the second one to the right. So if we, I guess, draw a picture here, I need to get out of my pen mode. So we would have a charge 1 here, and say charge 2 here, and they are 1 meter apart. So we could call this Q1, that Q2. We have a pretty picture of our situation. This is a 3 microcoulomb, and this is a 12 microcoulomb charge. Find the magnitude and direction of the net force on a -2 nanocoulomb charge when placed halfway between the two. So if I were to put charge 3 here, which was what? -2 nanocoulombs. If I put it halfway, so this distance is 0.5 meters. what does the force interaction look like? So the force on this, so the force of, say, charge 1 on 3, because that's not 13. Well, this K factor, so I'll just write K, and it's going to be charge 1, charge 3, over the distance between them squared. All right. Well, K equals 8.99 times 10 to the 9th. That's just the value of that Coulomb constant, K. So let me be clear here. K and K, that's what those two things are in the formula. And then, oops. We know that the distance between them is 0.5 meters. That gets squared. So that's in the denominator. And the two charges, I have a 3 times 10 to the minus 6 coulombs. That's charge 1. And I have a minus 2. Of course, we're just dealing with magnitudes, so I'm going to drop the signs. 10 to the minus 9 coulombs. So if you crunch all that out, you're going to get 2.16 times 10 to the minus 4 newtons. Now, which direction is it going to go? So here's the thing. These charges on the outside are plus, and the charge on the inside is negative. So in this interaction between charge 1, whoops, just realized I mislabeled that charge. This is charge 3. So what's the direction of the force attraction? What is charge 1 is attracting or repelling charge 3? It's attracting it, so it's going to be to the left. All right, that's one. So the way, just like in last semester, when you have multiple forces, you take a pair at a time, and you compute the force between those two objects, or in that direction. Then you take the other two, and then it gets added up. All right. So now we can do the other force, the force of 2 on 3. And it's going to have the same structure. I'm going to have 8.99 times 10 to the 9th as that Coulomb constant. And then we're going to have the same distance separation, just the other side of the situation there. And I'm going to have 12 times 10 to the minus 6 coulombs for that right-hand charge, charge 2. And then we're going to have the middle charge again in that computation. So F23, or the force of 2 on 3, is going to end up being 8.63 times 10 to the minus 4 newtons to the right. Well, the net force is just going to be the difference between the two. So basically, which one's bigger? Obviously, the charge on the right, the interaction between the right charge and the middle charge is bigger because the product of the charges is bigger. Okay, so the net effect is going to be to the right, and it's going to be the difference of these two things, these two values to the right. All right, so we would simply net force would equal F23 minus F13. And if you crunch those numbers, you should get, where did it go? 6.47 times 10 to the minus 4 newtons to the right. So simple net force calculation. So what are the steps? Calculate, well, Coulomb's law demands two charges. And you can do two and only two charges at a time when you compute an electric force. So if you pick a charge, we pick the one in the middle, that's what the problem is for, and you, all right, what's the force on that charge due to the first charge that isn't it, and this next charge that isn't it, and so forth, so on, until you're done with all the charges, and then you add it all up. Now in this one, since it was all along the same direction, it's just an arithmetic problem. Compute the force interaction between these two, compute the force interaction between the other two, and then the difference. Okay, or in this case, the sum, if you, because one of them was negative and one of them was positive. So we have our answer for part A. So I'm gonna section it off here. I'm a little bigger than I planned on. All right, so now what about if it's half a meter to the left of the plus 3 microcoulomb charge? So we can draw a picture again. So let's have our plus 3 microcoulombs, our plus 12 microcoulombs. This is charge 2. This is charge 1. And let's say that we put charge 3 out here. It's a minus 2 nanocoulombs. So we'll have half a meter here, 1 meter there. So if we do the interaction between these first two on the left, so the force of 1 on 3, again, it's going to be 8.99 times 10 to the 9th. And we're going to have 1.5 meters squared, and the product of those two charges. So that's going to be 3 times 10 to the minus 6 times 2 times, yes. Correct. Oh yeah, you're correct. Thank you. Thinking one thing, right another. So yes, we need to, that's only half a meter, it's not the whole distance yet. And so we crunch those numbers, and we will get 2.16 times, well, we already did this one. We didn't really need to rewrite all that, I guess, to the right. And then the force of 2 on 3, same constant, Coulomb constant doesn't change. This is the one that has the 1.5 meters in it. And we're going to have the charge 2 is 12 times 10 to the minus 6 coulombs. And then charge 3 again. The constant does have units that end up giving you back newtons, but I'm not going to write them in for efficiency today. 9.59 times 10 to the minus fifth newtons. It's also to the right. So why is it to the right? Well, those are two positive charges on the right. They both attract the negative charge, just at different distances. All right. And the one, even though the 12 microcoulomb charge is, 4 times as big as the 3, it's also 3 times farther away. So it ends up being a smaller amount of force, even though that charge interaction is bigger. And so really all we got to do now is sum these two. So if you add them, the net force is 3.12 times 10 to the minus fourth newtons going to the right. So the key thing here, every one of these computations is a simple computation. You're literally plugging in the known values and then adding them. The setup is essential. Unless you can track with it in your head, all right, you've got to have this picture. You have to draw the right picture and then use that force diagram, so to speak, to keep track of your mathematics. And unfortunately, we have to just take them a pair at a time. That's the way the law is structured. The mistake that you could make, besides just fat fingering the calculator or typing in the wrong numbers, would be when you do the net force computation. All right. And there's multiple ways to do that. You could use signs, and you could always add. Net force is always the sum of the forces. All right. And so in the part A, we're technically adding a negative. Or you could think of a subtraction. I did it in the way that was more qualitative based on I know it's going this and that direction. So I do the difference bigger minus the smaller. And since the bigger one is in the right, then it's all to the right. This last one, they both came out positive because they're both going to the right. Still adding them. So I kind of showed both ways to think it through. But that's where the problem comes, is if you're not careful in the accounting. But I hope you can see that algebraically this is not a challenging problem. But it's like any word problem. It's the setup. That's where you goof it. All right, so keep that in mind when you're doing the homework. Now we're going to continue this problem, except now I'm going to go evil on you and put an angle in it. This is why you took trig or pre-calc. Okay, we're going to use that math. So this still the same 2 charges or 3 charges as before, except now we're going to put that minus 2 nanocoulomb charge directly above the 12 microcoulomb charge, as shown in this picture. All right. So again, this charge 3 that we keep moving around, we want to know what's the force interaction on it due to the other charges. Just keep that in mind. That's what we're after here. So now we have to deal with this in X and Y directions. All right. So the distance, the charge separation, okay, Coulomb's law still, we can't lose sight of the fact that Coulomb's law requires that we have the product of charges, which I'll just call charge A and charge B, and the square of the distance between them. So that's a general statement. Instead of 1 and 2, I'm going to use A and B since we're using 1 and 2 elsewhere. All right. In general, that's Coulomb's law, must be obeyed, except it also it has a direction. As a vector, it has a direction. And we account for directions. One way to do that is sines, cosines, or technically cosines, but nothing there. So let me write this, and then we'll try to figure out what this means. So the charge, force 1 on 3. Now, in your textbook, I think they reverse the subscripts. Okay? It's the force between these two charges. If I want to think force 1 on 3, or the force on 3 due to 1, I could write F31. It'd be the same thing. So there's a little variability in what goes on here. This is going to be, again, this constant, 8.99 times 10 to the ninth. We'll just leave that there. And the distance squared. So here's the thing to think about. If I come over here, here's one leg of a right triangle, and here's another leg of that right triangle. Let me switch to, here's a distance, here's a distance. And so by Pythagorean's theorem, 1 squared plus 0.5 squared will equal, this c squared up here, if we pick that to be our c side. Well, guess what we want in Coulomb's law? We want that length squared. All right? So really what it comes down to is that I'm going to get 1.25. Right? Isn't 1 squared plus 0.5 squared 1.25? Okay? So I don't have to unsquare it. Because if I do the square root of, if I solve for the length, I get like 1.12 or something. But then I'm just going to square it back in Coulomb's law. All right, so I'm just going to use this number. So 1.25 equals c squared. So I'm just going to put 1.25, and it's square meters. Okay? It actually, that is the same thing as r squared. But what's being squared? All right? And if you wanted to, take the square root of 1.25. But why plug that in and just square it again? All right? You can do it, it'll work, but it's not necessary. All right. Back at the ranch here. And so then I'm going to have my charges here. So if I have a now 6, right? So we're going to have 3 times 10 to the minus 6 and 2 times 10 to the minus 9. Now, if I'm going to do the x direction, so I haven't put this in yet because I wanted to use the color, we need to do this in the x direction. Okay? I need the projection along the x direction. And so, but this is not going to change what Coulomb's law is demanding about, because you absolutely must put the square of the distance between the charges in Coulomb's law every time. Okay? But since we have more than one direction, we have a horizontal direction that it's acting, well, the way that we add it up has to be along the x and y directions if we're going to use rectangular coordinates. In this case, we are. We could use polar. That's kind of pushing the limits of this course, and we'd absolutely have to do it on a calculator. All right, we're still going to do it on a calculator. So I did this purposely this way to emphasize when you use Coulomb's law and you have x and y directions happening, you must use r squared is always the distance between the two charges. But if there's an angle involved, you're going to have to find what's the x part of that interaction and what's the y part of that interaction. And you're going to get that with cosines and sines every time. So the x projection is going to be a cosine projection because it's adjacent to this angle. All right. So we need the cosine of theta here. All right. So I'm doing extra writing because we need to be careful here. So this is this F13 along the x direction is still going to be this 8.99 times 10 to the ninth. I'm going to combine this stuff up top here. This is going to be 6 times 10 to the minus 15. 3 times 2 is 6. 10 to the minus 6 times 10 to the minus 9 is minus 15. So I'm just multiplying those two things. I'm going to have 1.25 in the bottom here, but my cosine is going to be 1 meter. Let me get my colors consistent here. Is going to be the 1 meter, the adjacent side, over the hypotenuse, which is 1.12. So over here, if we were to do that. So this, using the colors on purpose, there's always a component involved, but sometimes that component is 1 if you don't have a second direction. So now that's a fraction, that chunk. Because along the x direction, it's not the full. If I didn't put the cosine in, it would just be the separation distance. But that would only work if those were only two charges. All right? If there were only two charges, it wouldn't matter along what line that happens. It's just that's going to be the force interaction. But we're not paying attention to it along any line. We're paying attention in two directions. All right? So this works out to be, if you plug and chug your way, this is going to be 3.86, and I'm going to leave some space here because I'm going to put a negative sign on this, and you'll know why in a second. 10 to the minus 5 newtons. Now this is negative, and the reason why it's negative is because those are opposite charges. Their signs are opposite, which means this is an attractive force. And so 3, the charge 1, the 3 microcoulomb charge, we're paying attention to the force on 1 due to 3 along the x direction. That's what, when you see F sub 1,3 sub x, that's the force on charge 1 due to charge 3 along the x direction. All right? I'm going to change that x to green again because that's what we should have done. That's pretty lousy. Let's fix that. Which means I have to have that cosine component. So it's an attractive force towards the 3 microcoulomb charge. Hence to the left, and left is negative, right is positive, up is positive, down is negative. We're using standard Cartesian plane here. So we're banking on a lot of prior knowledge from math and the prior course. All right, so taking my time here. And you can watch this video again. There's other people doing videos like this too. So boom, we have the force of on 3 due to 1 along the x direction. All right. That's the only contribution that needs to get projected onto the x-axis. There are no other, because the force of charge 2 on charge 1 is straight line. Okay? But charge 3 is also, charge 2 on charge 3 is a vertical straight line. So we have that. So let's do, what's the force of charge 1 on 3 in the y direction? So anything that's at an angle will have an x and a y part. X components are going to be cosine, y components are going to be sine. So whatever thing is causing you the angle, in this case it's charge 1, you would know, expect in your head, I'm going to have to do an x part and a y part, or Coulomb's law with a cosine and Coulomb's law with a sine, because that one's out there. The 2 to 3 interaction is just one straight line in the y direction. There's no parts to deal with when we get to that one. So again, we'll have our Coulomb constant, and we could cheat a little here and just multiply. It's the same two charges, so it's still going to be this 6 times 10 to the minus 15, all right? Still going to have that charge separation of 1.25, okay? But this time, it's going to be the sine, so we'll say sine of theta down here, and that sine is going to be the opposite, so the vertical leg, the 0.5, over the hypotenuse of 1.12. And that will multiply out to 1.93 times 10 to the minus 5th newtons. And this is also going to be negative because it's pulling it down, right? So this will be negative. So that is correct. That's minus, well, it's 1.93 times 10 minus 5th in magnitude. It's a minus because of that. Another way to know that it's minus is you could just use the sign on the minus 2 nanocoulomb charge. Okay, it's gonna, that would make it minus. Okay, multiple ways to go about this. All right, so that gives us the x and y parts for this interaction caused by charge 1 on charge 3, because it has an x part and a y part to deal with. So the subtlety here, because it's common error, is putting the wrong distance in the bottom of the Coulomb law part before you do the sine cosine projection. Just want to stress that factor because, I mean, think back to your math class. How many times in some section of math you're going round and round, doing all your algebra right, but you just set it up wrong. So you got the wrong answer because you had the wrong setup, not the wrong algebra. Because I know you can do this algebra, just your setup, that's where you're going to biff it in there. All right, so continuing here. Now we need to get the force 2, the electric force of 2 on 3. It's all in the y direction. Okay, so I'll go ahead and put y. But that's where, once we do this one, we have all of the forces that need to get added up, so to speak. Right? So this one, same old Coulomb constant. And we're going to have, if you do the product here, I have a 12 micro times a 2 nano. All right. So 12 times 2 is 24. And a 10 to the minus 6 and a 10 to the minus 9 is going to give us this 10 to the minus 15 again. The distance separation is 0.5 squared. All right. In the last one, we could use the thing that was already squared, so there's a little bit of difference there. And there is no component to deal with. So you plug and chug on this and you'll get 8.63. This is going to be negative as well, times 10 to the minus 4 newtons in the y direction. And this is also minus. Two ways you can know it's minus. You know that charge 2 is pulling charge 3 down. That's negative. Or you could have used the minus sign in the charges. That because charge 2 or 3 was a negative. Okay. So another problem, I'll do it just using signs. The other one, this one I'm doing the direction qualitatively. So now I have all the force interactions accounted for. The 1 to 3 interaction has an x and y part because of where it's structured in the triangle. So maybe there's a thought process to go through. How do I know when to use parts? Well, if one of the interactions forces you to use an angle, then you must do x and y parts. If an interaction doesn't cause an angle, because it's directly in line along an axis, then it's just Coulomb's law straight up with no parts. That could be your decision rule. All right. Continuing here. Now we're going to net force this. So what you have is you have two x parts that can get added. So let me, you have two y parts that can get added and one x part. So these two forces are acting in the y direction. Okay? So since they're both along the y direction, I can add them. This other force up here, this is the only x force. That's all there is in the x direction. So when I do the net force calculation, let me kind of come off to the, so my net force is going to equal the sum of the x forces plus the sum of the y forces. Okay, now this is in rectangular notation. Okay, we're basically writing it like a vector. So there was only negative 3.86 times 10 to the minus 5th newtons. And then if you sum up these other two, you get where is it? These come out to minus 8.83 times 10 to the minus 4th newtons. Now, the subtlety there is like, wait a minute, how can a minus 1.9 and a minus 8.63 only be 8.83? Well, you're dealing with actually, that might be, yeah, that's correct. So let's be clear here. This is the x part, and this is the y part. In your homework, I ask you to find the magnitude. This problem stops with the magnitude and direction. So now I'm going to do two things to kind of set you up for that. One, if you look at your textbook examples, throughout their math, they're going to be using these little I hat and J hat unit vector things, all right? So technically, when we write the force law as a vector, we would have that unit vector thing. We haven't used that in a while, started that in the last semester. And one of the ways to deal with the x and y parts and z parts, one convention is to use I hat for x, j hat for y, k hat for z. Okay? So your textbook will show it that way. Lots of textbooks do it that way, but not all of them. Okay? And so really whether we have an I hat or j hat, or we just know it's x and y directions, is uh, important. So what I'm going to do here is I'm going to come in and say, otherwise you would think that you could combine these numbers. That's not k, that's j. You can't, before I put those I hat, j hat, meaning x and y directions on there, you should have been able to finish the deal and sum those numbers, but you'd be wrong. Okay? So it's another thing. I'm doing this problem excessively slow and pointing out all the weeds and potholes along the road here. You could very easily add those, when you sum all the forces, you can't add x parts to y parts arithmetically. You can only add x parts to y parts in a vector fashion, graphically. Okay? Easy mistake to make, and you could have done everything right except forget you can't add x parts to y parts arithmetically. 2 plus 2 is 4. No, not if one of the twos was aimed at x and the other two was aimed at y. You don't get 4 out of that. Okay? So be careful in that regard. So at this point, you wouldn't have enough to finish the deal. Here's how you finish the deal. You would square, okay, the x part, it's Pythagorean. So you would take the number for x, square it, the number for y, square it, add those two things and take a square root. That'll be your net. That'll actually be your net force in terms of its magnitude. So we're still not to the magnitude. All right? We're set up to do the magnitude. So I'm going to have to add a slide here to do this. You know, the strongest interaction is along the y direction. Okay? Because look at the other two forces have a 10 to the minus 5 multiplier, but that straight up and down 2 to 3 interaction is 10 times larger. Okay, so you got to realize when you're dealing with negative exponents, the smaller the exponent, the bigger the magnitude. All right, and so it's basically going to be 3 degrees off towards the middle. That's how you would interpret that 87 degrees. So basically the net effect, and this will make some sense, if I just do the parallelogram rule, assuming that these things here, you know the force is something like that. Now I don't think those forced arrows were they weren't scaled properly, but you know it has to be closer to the vertical than it is to the horizontal. All right, and it's going to be just 3 degrees off. All right, in that direction. So that's that. If you plug and chug all of that, you're going to get 8.83. Actually, it's going to be more like 8.84 times 10 to the minus 4 newtons. That's the magnitude of the net force. Okay? That's how strong it is. That's the force it feels, but we don't have its direction yet. You know it's not going to be straight at either of the other two charges. It's going to be somewhere in between them. But how do we do that? Okay, well, if you have an x and a y part of any physical quantity, x and y parts of a force, x and y parts of speed, I don't care what the measurement is in physics, if you have its x component, its y component, the inverse tangent of y to x will give you the angle every time. Okay? Now, in the homework, to keep it simple, I just had you compute the magnitude. All right? But we could, and we should, since this problem said it, what's the direction going to be? It's going to be theta, or the angle will be the inverse tangent of the y part of the force relative to the x part of the force. And so that's going to be the inverse tangent of, here's the y part, here's the x part, 8.83 times 10 to the minus 4th over 3.86 times 10 to the minus 5th. So that's going to be 87.5 degrees. All right. Now, relative to what? So you would, that means it's going to be pushed out. Well, it's going to be almost at that right angle. And that should make sense. So if, gets a little simpler here. Protons in an atomic nucleus are typically this 10 to the minus 15 meters apart. What's the electric force or repulsion between those electrons? So this is simple. Force is going to be, remember it's Coulomb's law, K, QA, QB, over the distance between them squared, so 8.99 times 10 to the ninth. And we're going to have, since it's a proton, it has just that fundamental charge, 1.602 times 10 to the minus 19 coulombs squared. And the distance between them is 10 to the minus 15 meters squared. So that means your force, crunch those numbers together, get 230.7 newtons. So 230 newtons. All right, so a newton is roughly a quarter pound. So 1/4 of this, let's get a firm number there. So 230.7 divided by 4. So heading towards 60 newtons. Somewhere between 55 and 60 newtons of force, okay? Or pounds of force. So think about it. 2 protons, insanely tiny, 10 to the minus 31 kilogram things, okay? And each one of them is feeling a force of 60 pounds, if you will, 50, 60 pounds, okay? 50 or 60 pounds, that's no big deal for us. That's like an oversized bag of salt rock or dog food or something like that. Bale of hay, a little bale of hay maybe. I think they're like 80 pounds. That's all, we can handle that because, we weigh somewhere between typically 100 to 200 pounds. Most people fall in that range of sizes. So for us, that's not a big deal of weight. It's not going to accelerate us very much. But for a proton with an insanely small amount of mass, just think about it. If I were to acceleration is going to be force per unit mass. And if it's talking about a proton, 9 point, I think it was 109, it's 9 point something times 10 to the minus 31 kilograms. Well, just think about it. When you do that math, okay, you're going to have, so 230.7 divided by, and I'm just going to divide it by 10 to the minus 31. You get roughly 2.31 times 10 to the 32nd newtons per kilogram, which would also be the same as 2.31 times 10 to the 32nd meters per second squared, or meters per second every second. Of course, that's much larger than the speed of light. You're not going to get a proton to go the speed of light, maybe 3 meters per second shy of the speed of light. That's our best so far. Okay? But that's insane. Okay? It's an insane amount of acceleration. So this, coming back to what I was saying earlier, the problem didn't ask for the acceleration that's on it. I'm just pointing out, no wonder there's so much energy packed into a nucleus. No wonder nuclear bombs are that explosive when there's that much energy packed into just 2 protons let loose. Okay, so strong nuclear force is able to keep this from happening. All right, that's good. Otherwise, we wouldn't be here. There wouldn't be any matter because nothing would stick. So it's impressive. That's a lot of. So 200 at first, 230 newtons doesn't sound impressive until you consider what that interaction produces in terms of motion. All right, or the relative how many force units per kilogram. It gets kind of crazy. All right, moving on. Now we're going to compare gravitational forces to electric forces here. So suppose the Earth and the Moon each carried a net negative charge, call it minus Q. And so we'll pretend that they're just huge point particles, all right? And let's remember the gravitational force is Newton's law for gravity. And the electric force has exactly the same structure, except you're dealing with charges. They're both inverse square laws, product of the thing that interacts in the field and a constant that relates those things one to the other. So those are prior knowledge things that bear in on this problem. So part A, what value of Q is required to balance the gravitational attraction between the Earth and the Moon? Okay, that means, in case you didn't catch it, to balance gravitational attraction between Earth and the Moon, what value of Q balances that? That means we're expecting that our gravitational force is in balance with our electric force. So what that means is I have G times the mass of the Earth times the mass of the Moon over the distance squared equaling K times, they have the same charge. They're both Q, so that squared over the distance squared between them. Okay, so that's what it means to balance. All right, meaning the gravitational force balances out with the electrostatic force. Since they're both negative, they both have the same sign charge, the Earth and the Moon in this case, that means they're going to repel one another, and we know that gravity is attractive. So if we put all this charge on the Earth and the Moon, equal charge, and then say, okay, how much should that be so that it exactly balances out with gravity? Okay. Um, Thankfully, nobody gets paid to do this in real life. That would be a challenge. So the distances drop out. Okay. You don't even uh, need them. And so what you end up getting, if you solve for Q, the only thing that's left behind is that K, which is going to switch to the denominator. So if I divide both sides by K, the K comes over here, and you just have the square root of, we could have the constants in ratio, and we could have then the two masses. Mass of the Earth, mass of the Moon. So, you may not recall, but the gravitational constant is 6.67 times 10 to the minus 11th. I'm going to skip on the units. K, we've seen that a few times already, 8.99 times 10 to the 9th. And then mass of the Earth, let's see here, that's 5.98 times 10 to the 24th kilograms, and the Moon is 7.35 times 10 to the 22nd kilograms. You crunch and munch all those numbers together, 5.71 times 10 to the 13th coulombs. Oops, do that. All right, that's a lot of coulombs. That is 10 trillion, 50, so it's going to be 57 trillion coulombs. 57 trillion electrons. All right, that's a lot. Now we know. All of our problems are solved. Part B, does the distance between the Earth and Moon affect your answer? Well, no. Got crossed out. We saw that up here. Distance didn't matter because the same inverse square applied in both situations. So we could drop it just by logic, or we could do it by math. We did it by math. All right, part C. How many electrons would be needed to produce this charge? I think I misspoke. Obviously, 1 coulomb isn't the same as an electron. It's a lot more. So I need to convert my 5.71 times 10 to the 13 coulombs to number of electrons. So I divide it by this definition of 1.6 times 10 to the minus 19 coulombs per electron. That means the number of electrons pops up to the top, and you get 3.56 times 10 to the 33 electrons. Okay, really large power of 10, largest one so far today, I think. That number, 10 to the 33, is 100 times smaller. Well, that wouldn't be a bad estimate for the number of grains of sand that comprise the Earth. If you busted the Earth down into 1 millimeter cube grains of sand, you would have about 10 to the 35 grains of sand. Just took the mass of the Earth, reshaped it all into perfectly sized grains of sand, you'd have 10 to the 35-ish. Okay, so yeah, we'd have to get a lot of electrons from somewhere. All right, that's it's hard to imagine powers of 10. Like if you take all the protons, electrons, and neutrons in the universe, there's 10 to the 80. That's everything. That's all the planets, all the stars, all the specks of dust in between. 10 to the 80 particles, elementary particles. in the physical universe. So powers of 10 really go crazy in that. All right, continuing here. Let's see. 2 fixed particles, 5 microcoulombs, 24 centimeters apart. What force do they exert on a third particle that has minus 2.5 microcoulombs? That's 13 centimeters. Well, we could, first off the bat, give you centimeters on purpose so that you have to convert it to meters. So this would be 0.24 meters, and this would be 0.13 meters. You should, otherwise you'll be off by a factor of 100 in your computations, assuming that those distances are needed. So what force do they exert on a third particle of charge that is 13 centimeters from each of them? So let's draw a picture. So here is my 24 centimeter separation, particle 1, particle 2, and I'm told that there's a third particle that's 13 centimeters from each of them. Well, that means it's got to be someplace like this. Okay, and so this is my 13 centimeters. So forcing you to draw a pretty picture. All right. So when we think about this, I'm going to have X and Y parts. All right. And remember that charges 1 and 2 are both 5 microcoulombs. And that this third charge is a negative half as much as that. So it's an attractive force. The two black, the charges 1 and 2, they want to pull that charge up because they're opposite charges. All right. So guess what? Nothing is along the interaction, or my system, charge 3, is what I'm concerned with. It has X and Y forces on it. The nice thing in this situation, because of the symmetry, is the X forces cancel out because they're equal and opposite along the X-axis. Yeah. So I have 2 Y forces parts pulling it up, but the X forces pull towards the middle. All right. So there's a, we get to drop the X forces cancel out. Okay. So X components cancel out, and that's because, you know, the X part here and the X part here, one's a plus, one's a minus, and they're the same size. So all of the charged products are the same. A 5 times a minus 2.5. There are no other charged products. So all the magnitudes are the same, but I have a plus 1 and a minus 1 for the X line. So they drop out. Same magnitude, different directions, 0 in the X direction, but not 0 in the Y direction. So my Y parts are both going up, and technically I should, I'm going to redraw my lines, and I apologize if you have pen, but this is better. All right, except I made that one longer. Try to So it has two x parts going opposite directions equal magnitude, so they drop out. But then there's two y parts, one from the left, one from the right. So we could say left, right. Man, I really gotta work on my penmanship here. And then this one's left and that one's right. So that, as you notice, the y's are going to add in a doubling fashion. So at this point, since I know it's only y direction and it's doubling, we can, well, one, let's just obey Coulomb's law first. So F in the y direction is going to be 8.99 times 10 to the ninth. And we're going to have a 5 microcoulomb force times a 2.5 microcoulomb force. And the separation distance is 0.13 meters squared. But it's at an angle, right? So we have to put our cosine in. So it's going to be our cosine of theta in this box here. And that's going to be I wrote 5 over 13. Oh yeah, it is 5 over 13. Sorry. If we were to, figure out what the sides of that triangle are, I have a 12 at its base, 13 on hypotenuse. If you do the Pythagorean thing, it's 5, 12, 13. You might remember those from the past. And so this works out to be 2.56. But I have two of them. Okay? So 2 times that. Okay? So that means at the end of the day, I'm going to have a force that's equal to 5.12 newtons. But what's the direction on that? And you would put your plus, your minus sign on there. So we had the magnitude. And I'm pretty sure that's the kind of question I asked you in the homework. Yeah, moving on. What if so we've gone from straight lines to triangles, right and not right triangles. What about the geometry of a square? All right. So hopefully you recognize that the diagonal of a square has to be root 2 times the length of the square. So how would you know that? Well, if you just had a 1, 1, 1 triangle, this is going to be root 2. 1 squared plus 1 squared is 2. Square root of 2 is square root of 2. All right, so that's why we can automatically, regardless of what the size of the square is, the diagonal is always root 2 times the length, the side of the square. All right, so we're banking on that prior knowledge of your calculus. And so that means that force components are going to have a cosine of theta equals 1 over root 2 factor. We just kind of know that in advance from the geometry. And so the net force I'm going to kind of set this up. This is going to equal, it's going to have X and Y parts. So I know in advance that I have some chunk going in that I direction. And I have some other chunk going in the Y direction. I keep getting my J's and K's. There we go. I know in advance that I'm going to get something that's associated with that X direction or I hat, and I'm going to get something associated with the Y direction or that J hat thing. So again, this is the setup because the math that's about to go in these boxes is not that hard, but what to expect. What should you expect? I expect an X and Y parts because I'm looking at this, and what's the force on charge Q at the lower right-hand part? So let's help ourselves out and say, this is our system. That's what we're paying attention to. Okay, is what's the force on that charge that I highlighted in red? Well, I have a straight line Y force for the one above it and a straight line X force for the one to the left of it. Absolutely know that those are easy. It's just going to be Q squared over A squared times the K factor. Coulomb's law again. Okay, so remember, in general, Coulomb's law is QA, QB over the distance AB squared. We know that's going to be that way. So here in the first part, along the X direction, I've got just Q squared over A squared. That's applying Coulomb's law just to the this one here. So this part is dealing, I'll use my colors here. I just drew in what applies there. Now I'm also going to have this other part, so the top left corner is going to be a K, still Q squared because it's a Q and a Q interacting with one another. But what do I get? I still the diagonal is the same in both directions, okay? So if I take the square root of 2 times A and I square that distance, what do I get? Well, the square root of 2 squared is 2, and square root of A, or the square of the square root of 2 is 2, and the square of A is A squared, so I just get 2A squared. But it's at an angle, and we already figured out the bonus of the square is that it's always the same component. And so I'm going to have times 1 over root 2. Now you might remember in math class it was bad to write 1 over a square root. Yeah, I don't care about that. Physics, we don't care about that. Could we write root 2 over 2? Sure. That makes you happy, do it. But we don't have to obey some of the dumb rules that math made you do, okay? Because computationally, you get the same number, however you write it. So that's that. So guess what's going to happen? Do you expect the y connection to be any different, given that it's a square? The square is symmetric, pretty much no matter how you slice it. Slice along the diagonals are symmetric, and that's pretty much what we're doing here. So, but let me be careful though, since I highlighted one. That's what this one is referring to. Okay, so we end up getting the same exact thing out of the other one. So we'll get a K Q squared per A squared plus a K Q squared per 2A squared 1 over root 2. Just flip it around, it's the same two things, okay, in the Y direction. All right, and that's it. We can't do any more with this. I don't have any numbers. I don't know how long A is. I don't know how big Q is. I could put the 8.99 times 10 to the ninth, and that would help me. So this is just a totally theoretical problem with nothing to compute, just a model. Sometimes that's all we do is just build the model, and if I know A and I know Q, then I'm done. Right? So that's that, and I'm gonna stop. I'm gonna stop right here because this movie has now gone an hour and 45 minutes. All right, this particle with 2 times 10 minus 8 coulombs experiences upward force, magnitude of 4 times 10 to 6 newtons when it's placed in a particular point in an electric field. So remember, electric fields are defined as force per unit charge. I said it again. I said it before. I'll say it again. Any field strength is always that force per unit, whatever mediates that force. And so in gravitational fields, it's force per unit mass. In electric fields, it's force per unit charge. When we get to magnetic fields, it'll be force per charge times speed, because a charged particle will only feel a magnetic force if it's moving. Otherwise, it won't feel it. More on that later. All right. E equals F per Q. So the force, this is simple. 4 times 10 to the minus 6 newtons over 2 times 10 to the minus 8 coulombs. You're going to get a whopping 2 times 10 to the minus 2 newtons up, as it already said, but that's because it's an upward force. Part B. If a different charge is placed there, what's the force on it? Well, force is also charge times field. Big Q or little QE, it doesn't really matter. It's just discombobulating the definition. And so a minus 1 times 10 to the minus 8 coulombs times that force, I'm sorry, newtons per coulomb, there we go, times that field strength we just figured out. And so the force on this one will end up being 2 times 10 to the minus 6 newtons down. That's because of the sign. That negative sign pops it down. Right? Easy peasy. So these problems come from sections of a chapter. So within a section, you might have easy and hard, and then you have a next one that's easy. Yeah. Oh yeah, that should be +2. Thank you. Yes, that would make it a +2. And this should be, yeah, so it looks like I had it right in one, but not the other. All right. That would give me a -6 in the bottom one, so. All right. Consider an electron that is, well, this should be 10 to the minus 10 meters. Didn't get I thought I caught all of these. So sorry about the typos. So an angstrom, I think 10 to the minus 10 meters is an angstrom, typical atomic scale. Alpha particle has a relatively small charge, not much more than, well, it's double of elementary charge, and helium has 2 protons there. So all right, what does the electric field do to the alpha particle at the location of the electron? All right, so electric field is what you've seen before, K times the charge over the distance squared. And that's just Force per unit charge is what electric field is, and when you divide charge out from Coulomb's law, you get one less charge. It's exactly like Coulomb's law, just one of the charges is not listed there anymore. And so we plug in Chugsville. So 9 times 10 to the ninth times the charge that we're paying attention to, so the 3.2 times 10 to the minus 19 over the distance squared. And that gives us a very large field, 2.8 times 10 to the 11th newtons per coulomb. Electric field strength is also measured in volts per meter. Volts per meter are the same thing as newtons per coulomb. Just volts is a different, the ratios says sort of like newtons per coulomb and meters per second squared. They're fundamentally the same thing, just depending on how you're looking at it. What's the electric field due to the electron at the location of the alpha particle? Okay, so electric field is going to be 9 times 10 to the ninth, but it was electric field due to the electron at the location of the alpha particle. Well, the charge on the electron is just this simple one. Still, the 10 to the minus 20 is what that distance squared is going to be. And so this one is 1.44 times 10 to the 11th newtons per coulomb. They're on par with one another. So remember, in the electric field equation, what's the electric field due to fill in the blank? Well, the charge of fill in the blank is what goes into that formula. And the distance that that thing is from whatever is going to feel that field effect goes into the formula. Okay. What is the electric force on both of these doohickeys? So, so I'll kind of do the force for part A. So the force on the alpha particle will be the charge on the alpha particle times that field. So 3.2 times 10 to the minus 19 coulombs times the field due to the electron. So if we're talking about the alpha particle, okay, the force will be the charge of that particle times the strength of the field that's acting on that particle, and the field that's acting on the alpha particle is the electron's field, not the alpha particle's field. No charge feels the force of its own field. Charges feel the force of some other particle field. Make sure that you never self-reference a charge to its field. It doesn't feel a force from itself. It feels forces from other fields. So this works out to be 4.61 times 10 to the minus 8 newtons on that alpha particle. And for B, the force on the electron is going to be the fundamental charge on an electron times the electric field that we were dealing with, which would be of the alpha particle. So I guess I should put of the electron up there. And 1.602 times 10 to the minus 19 times the other field, the 2.8 times 10 to the 11th newtons per coulomb. And this works out, surprise, surprise, but when you look at the numbers, one of the charges is double of the other, and the electric field is double of the other, so the products work out. You can kind of look vertically at the blue and the green, you see that the doubles balance each other out. Lucky us. Oxygen nucleus. What's the electric field of an oxygen nucleus at a point, an angstrom, away from the nucleus? All right. So E would be our kq per distance squared. So I'm going to write this, and then I'm going to say something. What goes out in front of that? Realize that 1.602 times 10 minus 19 is fundamental charge units. Anybody know how many electrons oxygen has? 8. What's that? It's 8. Well, it has a charge of, it has 8 of those fundamental things. So 8 is this number. You'd have to look that up. And what would be wrong here is if you didn't think, oh, I need to count the trons, okay, you would just have something that's 8 times smaller than it should be. All right, so subtle. Professor is tricksy. Wants to kill us, he does. All right. So 1.15 times 10 to the 12th newtons per coulomb. What's the force? What is the force this electric field exerts on a second oxygen nucleus placed at that point? Okay, so the force, again, is just going to be charge times the field. And we're going to have 8 times that fundamental charge. And the field we just solved for. So the force works out to be 1.47 times 10 to the minus 6 newtons. Really small force, as far as we're concerned, but for an atom of that size, that's a lot of force, as we saw in that other example a little bit ago. All right, point charges. One's a 50 microcoulomb, one's a minus 25 microcoulomb. They're 1 meter apart. What's the electric field at the midpoint between them? Okay, so the electric field. So we'll have our 9 times 10 to the 9th K factor going on there. But we need to sum up the influence of two charges producing their fields. We need to add that up. So on the left-hand side, we would have our 50 times 10 to the 6 coulombs acting at a distance of 0.5 meters squared. And on the right side, just from a magnitude standpoint, the 25 microcoulombs at the same distance. Now, I could have written this field equation twice. I could have wrote the field of one plus the field of the other, or I could just add them because they both have the common factor of the constant. Okay, so this is basically if this is charge 1 and this is charge 2, this is E1 and E2. And they both have their K factor extracted out. So what's the electric field at the point in between them? Well, that just accounted the two distances squared, accounted for the point in between. And this crunches all out to 2.7 times 10 to the 6 newtons per coulomb. So this is a superposition, netting of the interaction, be it a force or a field, whatever, field strength in this case. You could have just done them separately and got the same answer, or you could write it out this way. That's a lot. That's almost 3 million newtons per coulomb. All right, that's a lot. What's the force of some charge that we would stick there? Well, if the field strength at that location is what we just computed, then the force on it will just be that charge times that field. So 20 times 10 to the minus 6 coulombs times that field strength, 10 to 6 newtons per coulomb. And so your force works out to be 54 newtons. Again, we just, I don't know, hour ago, that one problem where the force on an electron or something was basically a large force like this. And so this would be a lot of force on something like that. Okay, so